So in this video, we start a new block of the class. We're done talking about limits, at least for a little while, and we're moving into integration. I call it an intro to integration because we're going to be spending a lot of time dealing with integration. You could argue that integration is really the whole purpose of this class. Calc 2 was sometimes called integral calculus, integral referring to integration, what we're going to learn here. And the idea with integration all boils down to one simple question. How much area is there underneath some given curve between two given points? That's what I'm trying to illustrate here. If you're given some curve, I'm just going to generically call it f of x here, and two different x values are specified. I'm going to refer to those as a and b. A is the beginning x value, b is the ending x value. If I have a curve and two different x values, that defines some area. And what I want to know is how much area is it? That's it. It sounds like a fairly basic question. How much area do you have right here? But it turns out that it's a really complex question. Answering that question is not only difficult, but super duper important. All of Calc 2 will be based upon that question. And what we're going to do in this video is going to get an idea about how we're eventually going to answer that question and how we're going to start out answering that question. And the difference between the two is eventually we're going to calculate this area exactly. But right now, we're just going to estimate it. And that might not make any sense. Like, why would you estimate it if you're going to later tell me how to calculate it exactly? And the answer is the way we're going to calculate it exactly will be based upon the estimates that we do. So even though it's a little counterintuitive, it'll be really important to understand how to estimate the area because we'll use that to calculate it exactly. Without further ado, let me show you how we're going to estimate it. The way we're going to estimate area is we're going to think back to formulas you know for area. And you're like, pi r squared. Good, right? That's the area of a circle. That's good that you know that. It won't help us here, but it's true. 1/2 the base times the height is the area of a triangle. Also not helpful here, but true. What you need to know is probably the most basic area formula you ever learned. The area of a rectangle. Right? If I give you a rectangle and the rectangle is 8 by 10, and I ask you how much area that rectangle encloses, it'd be awesome if you knew the answer was 80. Right? The area of a rectangle is just the length of the base times the height. And using that knowledge, we'll be able to estimate the area underneath this curve using rectangles. So what we're going to do is we're going to be told how many rectangles to use. For the sake of this picture, let's choose a small number to make my life easy. Say we want to estimate the area underneath this curve with, I don't know, 3 rectangles. We want each of these rectangles to have an equal width. So what I have to do is I have to take the area from A to B and I have to break it up so that it kind of houses 3 different rectangles. And the way I do that is I choose 4 points. And I'm going to call those points x0, x1, x2, and x3. And that might seem counterintuitive that I have 4 points, and 4 points is going to define 3 rectangles. But I think when I draw the picture, you'll see what I mean. Here, right on A, is what I'm going to call x0, or x0. And here, right on B, is what I'm going to call x3. And in between those, I need x1 and x2. So I'm going to evenly space these out, so that x1 is somewhere in there and x2 is somewhere in there. And hopefully you won't argue too much. These are supposed to be equally spread out. A, our starting point, will always be x0, and B, our ending point, will always correspond with x and the number of rectangles that we have. And in this example, we're going to have 3 rectangles, so it's x3. And yes, that's 4 points, but as you see, it makes 3 rectangles. These will be the base of our rectangles, and they're all the exact same. That's important. Now what I want to do is I want to figure out the height of the rectangles. And there's 2 different ways you can do those. Let me first draw you a picture showing how you figure out the height using left endpoints. Here's the picture as best I can draw it for estimating the area underneath this curve using 3 rectangles, and the heights of the rectangles are based on their left endpoints. What do I mean by that? Picture this first rectangle whose base goes from x0 to x1. This first rectangle, its height is based upon this point. This point is the left endpoint of this rectangle. I didn't make the height up here or somewhere in the middle. I didn't make the height way up here. Maybe you can imagine this first rectangle being this high. It would be that high if I based its height based on its right endpoint. But I didn't. I based it off its left endpoint, so its height is just this high. The second rectangle, whose base goes from x1 to x2, I based its height off this point, the left endpoint of that rectangle. Similarly, my third rectangle, its height is based off this point, which is the height at x2, the left endpoint of the rectangle spanning from x2 to x3. Some notation. What I drew right here is L with the little 3 in the subscript. L, because I'm using the left endpoints to estimate the heights. 3, because I have 3 rectangles. When I'm figuring out L3, I will need 4 different x values. Those x values will go from x0 to x3. That's 4, but I need 4 to create 3 rectangles. I'm going to give you formulas for how to figure out all these different values, for how to estimate these, for how to find these areas, but that's not the purpose of this video. Here's another function. I'll call it g of x now, just to differentiate it from f of x, which we saw above. I'm also given an a and a b. Again, I want to figure out how much area is underneath this curve, g of x, between these two values of x, a and b. Suppose instead of drawing the picture for L3, I was asked to draw the picture for R4. 4 is telling me I'm going to want 4 rectangles. To define 4 rectangles, I need 5 points. Those points are going to be x0, x1, x2, x3, and x4. x0 will correspond with A, as it always does. x4, x with my largest subscript, will correspond with B, as it always does. And then I need to find x1, x2, and x3 so that those dots are all equally spread out. Let me try my best to draw the picture of where they'd be if they were equally spread out. x1, x0, x1, x2, x3, and x4. If I am drawing rectangles, if I'm drawing 4 rectangles, I need these 5 points to define the base of the rectangles. If I am asked to use right endpoints to figure out the height, then for this first rectangle that goes from x0 to x1, I want to figure out its height based on x1. Remember, up here for my first rectangle that went from x0 to x1, I figured out the height of that rectangle based on this point, x0, x0, because they were left endpoints. Down here, my first rectangle that goes from x0 to x1 is only going to be this tall. Its height is going to be based on the height at x1, not the height at x0. Using similar logic, we get this picture. Here is the picture for R4. R4 is an estimation of the area underneath this curve, g of x this time, between A and B. And to come up with that calculation, what I need are 5 different x values, x0, 1, 2, 3, and 4. And using those 5 different x values, I need to define rectangles. And the heights of those rectangles are based on their right endpoints now, not their left endpoints. And if you follow all that, you got just about all the notation that I need you to get out of this video. The one other thing that I want to add is the distance between any two x values is supposed to be the same. Right? The distance from x0 to x1 is the exact same as the distance from x1 to x2, x2 to x3, and so on. It'll be useful to have a symbol for that. The symbol we're going to use is delta x, a triangle and then an x. So the distance between any two x values, between x2 and x3, or x3 and x4, any of those, is delta x. So as far as terminology goes, when you see L3, I want you to know that this is somebody asking you to estimate the area underneath the curve using 3 rectangles. To come up with 3 rectangles, you need x0, x1, x2, and x3. And the distance between any two consecutive x values is a symbol delta x. And if you can follow all of that, I know it's a little bit symbolic heavy, but if you can follow all of that, you'll be able to do examples. I'm going to do some beginner examples in the next video. And you'll be like, this is really, really easy. I could have done those beginner examples without all this notation. But what you'll see is you need all this notation. And the reason why is because we need to fix this. This is wrong. The area underneath the area of the red rectangles is not the same as the area underneath the green curve. The area of the blue rectangles is not the same as the area underneath the green curve. It's just an estimation. But you know what? We can make that estimation better and better. And the way we do it is by choosing to come up with more and more rectangles. This is a pretty poor estimation, right? Using 3 rectangles to figure out this area is far off. It doesn't include all of this up here, but it over adds in all this up here. It's way off. But we can make it a lot better if instead of using 3 rectangles, we use 30 rectangles. Your book does a good job of showing you that picture because I sure as hell don't want to draw 30 rectangles. Here's a curve, and your book estimating the area under that curve with 10 rectangles, R10. Right? Using right endpoints, if you look really, really carefully on any one of these rectangles, it determines the height based on their right endpoints. And they're using 10 of them. I think this is the curve y equals x squared, but it doesn't even matter. They're giving you some curve, and they're estimating the area under the curve with 10 rectangles. And you're like, yeah, I guess that's okay. That's an estimation, but it doesn't look great. Right? The area of the rectangles doesn't really look like the area underneath this light blue curve. Looks a lot better over here, right? Because they use 30 rectangles. Here's R30. Here's R50. Similarly, here's L10, L30, and L50. The key thing to note here is now the height of the different rectangles are based on their left endpoints, not their right endpoints. And what you're going to end up doing is you're going to come up with an expression that represents any one of these guys. At first, we're just going to figure out the area. We're just going to figure out this plus this plus this. You'll get some answer, you'll be done. Be like, this is 3, this is 6, this is 5. 3 plus 6 plus 5, that's 14. 14 is my answer and I'm done. Yeah, all right. I mean, 14 estimates this area, but we can't really make 14 any better. By leaving these as numeric estimates, we can't make them any better. But you know what we could do is we come up with a formula that tells us the area for any value of n, right? A formula that tells us the area when n is 10, or when n is 30, or where n is 50, where n represents the number of rectangles that you have. And then, using what we learned in the first half of this class, we could take the limit as n approaches infinity. Because if we have infinitely many rectangles, they're infinitely skinny, right? And they're so skinny, it doesn't really matter if I use their left endpoint or their right endpoint to estimate the height, because they're so skinny that the left and the right are right on top of each other. And because they're so skinny, the height of each one perfectly lines up with the curve that I'm interested in here. So if I could calculate L infinity, which I'll be able to do by coming up with an expression for Ln and then taking the limit as n approaches infinity, I will have an answer to the big question that we're looking at integration. The good news is that's a little ways away. Right now, we're just estimating. We're not going to take any limits. We're not doing any of that. But I wanted to really emphasize why I'm giving you so much notation, why I want you really good with the symbols, because nobody cares about an estimate for the area underneath the curve. What we want is an exact value for the area under the curve. And you can only get that if you can represent your estimation with an expression. Think letters and not numbers. That's what we'll be doing in the next couple sections. And it might be a little bit intimidating right now, but it turns out to be kind of interesting and kind of fun. Maybe I should have quit the video before I said that.